Hello, this is Math 2270 coming to you from the College of DuPage for the summer of 2020. And this is the lecture entitled The Inverse Laplace Transform. Again, to make it clear where we're going, we're using transform methods and the Laplace transform to help us solve differential equations. And so we want to find an unknown function y of t that satisfies a differential equation and initial conditions. And one way to do it is to apply the Laplace transform and transform the differential equation into an algebraic equation in capital Y of S. We use algebra to solve that transformed equation for capital Y of S, but then we have to apply the inverse Laplace transform to get back to the original y of t for our solution. Previously, we talked about this. Today, we're talking about this, and you know all about algebra. Now, in mathematics, the inverse Laplace transform of a function capital F of S is a piecewise continuous and exponentially restricted real function lowercase f of t, which has the property of, when you take the Laplace transform of lower f of t, you get capital F of S. Now, it was proven, this is called Lurch's theorem, that if a function capital F of S has the Laplace transform f of t, then f of t is uniquely determined, except on a set having Lebesgue measure 0. And that was proven a long time ago, and it was kind of an important theorem. Now, you might say, I would like to have a formula for the inverse transform. Well, an integral formula does exist for this, and it's called Mellon's inverse formula. It's called many names, actually, but when you look at it, it is f of t is equal to 1 over 2 pi I. Yes, that is I, the imaginary number. It is the square root of minus 1. And then this is the limit as t goes to infinity of. And this is a line integral, going from this complex number to this complex number, but taking the limit as t goes to infinity of e to the st times capital F of st ds, and the integration is done in the complex plane, and there are restrictions on the singularities and regions of convergence and so on. And in practice, this is done using the Cauchy residue theorem, and this is all complex analysis that is being done. There's also a post-inversion formula for Laplace transforms, named after this guy. He wrote this paper in 1930, and this is a simple-looking but usually impractical formula for evaluating it. He proved that under general conditions like this, f of t is the limit as k goes to infinity of minus 1 to the k over k factorial. This is k over t to the k plus 1, and that is the kth derivative of the transform evaluated at k over t. And again, this is impractical to really evaluate that for almost any type problems. And more recently, by the way, this is a great little boutique engineering school that I know of. This guy, Kurt Bryan, who teaches there, wrote a little paper about elementary inversion of the Laplace transform. Now, the takeaway of all this is you're feeling around some pretty serious math here. It's good math, but largely beyond the scope of this course. Your task is simpler. We use tables with results like this theorem that's in your book. And so we prove what all of these inverse transforms are. But the way we prove it is the inverse transform of 1 over s is 1 because the Laplace transform of 1 is 1 over s. Similarly, the inverse transform of this expression in s is t to the n because the Laplace transform of t to the n is this expression in your table. We know that the inverse transform of 1 over s minus a is equal to e to the at, because if I take the Laplace transform of e to the at like we did last time, I get 1 over s minus a. We also did this one, I think. The inverse transform of this expression is sine kt because the Laplace transform of sine kt is equal to that expression. I think you get the drift. So in evaluating inverse transforms, it often happens that a function of s under consideration does not match up exactly with the form of the Laplace transform given in a table. It may be necessary to fix up the function of s by multiplying, dividing by an appropriate constant, or other kinds of things like completing the square. Okay, and a most useful tool in fixing things up is to match the table as found in the following fact that the inverse Laplace transform is linear. So it satisfies this equation. So let's compute some of these. This is example 1. And what you want to do is use your table to find the inverse transform of each of the following. You're looking in the f of s column and trying to match it with something else. You got 1, 2, 3, 4 problems here. You know what to do. Let's see how you did. So here, what you're going to do is you are going to use the linearity, and so you're going to say, oh, I'm looking for 1 over s. I'm looking for 1 over s minus a constant. Well, when I look here, I say, oh, that's going to be associated with 1, and this 1 over s minus a is going to be associated with e to the at. So it's linear. So the 6 just sits there. I invert the transform here, and I get 1. The minus 1 just sits there. I invert the transform and get e to the minus 8t. And the 4 just sits there. I invert the transform and I get e to the 3t. I simplify it, and that is my answer to problem example 1a. Example 1b looks like this. Now, when I start looking at this, trying to match things up, I see, oh, well, I'm looking at s plus 2, and that matches up pretty well with this one. And this is, except for a constant, that is s minus a, so I'm pretty good with that. Now here I have s to the 5th, and the closest thing to matching up with s to the 5th is formula 3, which has this on it. Okay, so the constant just sits there. I call this s minus a minus 2. The minus 1 just sits there, and I do factor out a 3 because this doesn't have 3s minus 3a or 3s minus 5. What this has is s minus a. So I factor the 3 out, but now I have this in the form where it matches the table. And here, you see it really doesn't match up. I got s to the 5 here, but I need an n factorial there. So what I do is I multiply by 4 factorial and I divide by 4 factorial. Then I simplify. The 19 just sits there. This is 1 over s minus a minus 2. This is minus 1/3. This is 1 over s minus that. The 4 factorial is listed down here and up here. And then I'm going to invert all of these. Well, when I invert this one, I get 7 over 24. That's the constant, t to the 4th. When I invert this one, I have the minus 1/3. It just sits there. This is e to the 5 over 3. T, and this, the 19 just sits there, and this is e to the minus 2t. Let's look at this one. Now, again, I'm looking in my f of s column over here, capital F of s, and I'm saying, oh, those kind of line up with these two functions, and so that's what I'm looking at. So the 6 just sits there, and I have s over, and that is going to be a squared. And this is going to be, and what I really want to have here is I want to have 5 over s squared plus 5. I don't have it, so I have to multiply top and bottom by 1. I multiply top and bottom by 5, and that's multiplying by 1. And so what I get is 3 over 5 times this. And then I'm going to invert both of these transforms. The 6 just sits there. When I invert this using my table, I get this. The 3 over 5 just sits there. When I invert it, I get this. One more example. This one. Again, I have this kind of expression showing up there, except for a constant that I can factor out. But now I have s squared minus 7 squared, and so that actually is this, a different formula that we haven't looked at before, and this is the hyperbolic sine of at. Okay, so let's have at it then. So capital G of s is, I factor out the 3 to make this match up exactly with the table. And I come over here and I have to, I need a 7 here. So I multiply by 7 and divide by 7, not changing anything. And then I can factor things out. So this is going to be 4 over 3 times when I invert the transform, it is sine of 2t. And this is going to be 3 over 7, and that's going to be the hyperbolic sine of 7t. Okay, here's another problem for you to do. You want to find the inverse transform of all the following. These get a little bit more involved. You know what to do. See how you do in 26.